from the College by the Lake, Coeur d'Alene, Idaho. Local, regional, national, and international guests discussing the issues and topics affecting the way you live are on Forum, the North Idaho College Public Forum, with your host and moderator, political scientist Tony Stewart.
We're going to bring you a 2-week series starting today on what one could describe as a very fascinating set of topics. Today's program is called The Solar System Exploring the Planets, and next week we'll come back and even deal with the larger question, and that is the universe, and some people would even contend the black holes are into different universes. We're very fortunate to have 2 guests on our program today and next week. Both are members of our faculty at North Idaho College, and they are distinguished in the work they have done on a number of subjects. First of all, I welcome to the program Kurt Nelson, who holds a BA degree in the field of math from the University of Washington in Seattle and an MS degree in physics from the University of Idaho. Next to him is his colleague and our colleague, Lloyd Marsh, who holds a BS degree in chemistry from the University of Idaho, and his MS degree, and I should say his BS is in chemistry, and he has an MS in electrical engineering from the U.S. Naval Postgraduate School. My colleagues, welcome to the program. We're happy to have you here, and among other things, we're going to show some slides so that our viewers can appreciate something called astronomy, and thank you for taking the time.
My pleasure.
And as always, I'm very pleased to have regular panelist Steve Schenck, who is the Dean of College Relations and Development at North Idaho College, and we're going to do a little different format in starting out today so our viewers can, I guess, have what we call a visual background before we get into questions with Steve and myself. We're going to ask you, Kurt, I believe, to take us through some slides that you've brought, and we're going to look, I guess, at some of the questions about the sun and the 9 planets around it, and asteroids and meteors and the moons and the early history, and all about sky and the Earth and its atmosphere and other such questions. So at this time, if our staff will put up the first slide, I'll have you to walk us through. I believe we have about 7 or 8 slides to commence the program.
Okay, the first slide you see here is a photograph of our sun, of course, the giver of life, and this is taken with a special X-ray photograph. Shows the convoluting or the complexity of our sun, not like what we usually see or visualize in pictures. The next slide probably would be another slide of the sun, and it would show a prominence or the magnetic field structure of the sun, and we have to study our sun as a curiosity, or trying to find out how long it will last and what the dynamics are of the sun, etc. It's a difficult thing or an object to study because you can't see down inside of it. You see in this slide that there's a prominence or a big parabolic arc going out from the sun, and also it has a different character, so it's actually taken with a different kind of a light. The inner planets are always very interesting to think about as we survey the solar system. The inner planets have a higher density, like our Earth, and they're called the terrestrial planets. We have Mercury and Venus. I'm going from the sun out, and then we have the Earth and Mars. And you look at the blue marble in space, you compare it to other planets, you find that each planet is different in its character. Venus is about the size of the Earth. Mercury itself is on the right, very small, it's closest to the sun, and it has no atmosphere at all. The Earth, we kind of think we know what's going on with the Earth, but it's nice to see pictures of it. It has a marbling of the atmosphere, it has water on it, which is unusual, large bodies of water. And then when we think of Mars, Mars is actually a barren planet now, but it had water at one time, hardly any atmosphere, has polar caps, and it has some of the largest physical features in the solar system when it comes down to mountains or valleys. It's also historically nice to think about all these planets as being related to gods at one time by our ancient cultures, and that the 5 days of the week plus 2 more make 7, which is Sunday and Monday, which might relate to the sun and the moon, and then 5 more. The outer planets are less dense, and they have forms like gases. The very large one, Jupiter, the largest that we have, with a giant storm on it that's been there for 250 years. The beautiful planet Saturn with the rings around it. These are very light planets in structure. Uranus also is farther out as we go. And we're going a long ways out here, folks. This is about 40 astronomical units by the time we get to Pluto, which is 40 times the distance from the sun to the Earth. When we get out to Pluto, we've flown by close, but we don't know a lot of information other than it's very cold and rocky. Neptune is, of course, quite a ways out, and Neptune, Uranus, and Pluto weren't discovered until later in history, after 1850. So each planet has its own character, very cold, and if you look real close at a planet, if you flew by it, this is a picture of Venus. Venus has been covered with clouds. We can't see into it optically in the years past, but through radar imaging, etc., we can get more characteristics of it with special imaging techniques. Jupiter, if we look at Jupiter, you can see on it striations, and it's a very large planet. Also, you have the great storm, the red spot that was kind of unusual. You can see it as you look at it, rotation, which causes horizontal lines, and you can see a lot of turbulence. And there really isn't much about the surface of Jupiter. It's a very large planet with many, many moons, as we found out later on. Galileo looked up early in the 1600s and found some moons, 4 of them, in fact, with a toy telescope from the Netherlands, and found 4 moons that are called the Galilean moons. And you can see on this slide 2 of the moons, 2 little circles superimposed on the giant planet as they go around, Io and Europa. Another slide shows Uranus, which is a blue marble in the picture, and shows a few moons of this planet. Now, this planet is blessed with more moons than we have, just being one, but I want you to note in particular that each moon has a different character or structure. It's a wonderful mystery to study about why are all the moons different. I think that possibly that would be the best thing that I could do to survey the solar system for you folks and our viewers, and it's an interesting study, and a lot of people don't know too much about the solar system, and I think that's the best that I can do in a short time.
Thank you.
Yeah.
We'll turn to Steve Sheen.
Lloyd, maybe I could just kick things off with a sort of a non-scientific, well, maybe it is a little bit scientific, but more of a philosophical question, and a real general one at that. And that is, those were beautiful pictures, and it is fascinating to look up at the night sky and identify planets and stars. But what value does the study of astronomy have for people?
Well, you know, if you're looking into the future about 4.5 billion years when we think the sun will burn out, it means that we better study some other places to go. And, you know, if you're looking at it from a very practical point of view, but 4.5 billion years is a few years away. But I think, if nothing else, it's to satisfy the human curiosity. When we go back into the ancient civilizations, the Greeks, the Mayans, many of the civilizations, as they evolved into a civilized society, certainly looked towards the night sky, where we could see things that were external to the Earth's environment. And this sparked what I believe is a human trait, a curiosity. And of course, entire cultures grew up around the curiosity and the answers that we humans came up with to explain the manifestations that we saw in the sky. We have since gone a long way from that as we go from the philosophical bent of satisfying curiosity to some of the very practical things that we deal with. Now, as we go into space and study the solar system and so forth, much of the technology that we enjoy today has evolved from that effort. You know, if something very simple like Tang, this drink that we developed for the astronauts, but in a more practical sense, there are many spin-offs from our innate curiosity to study that. And so I think there's just a great expanse of material to be benefited. And first of all, I think it satisfies our curiosity.
Kurt, Lloyd touched on something that we talked about briefly before the show started, and that is the fact that there are many ancient cultures that drew some part of their day-to-day activity from their rudimentary knowledge of the sun and the stars. Could you give us some examples of those cultures?
Certainly, some of the cultures that looked up to the heavens were the Greeks and the Babylonians, the Egyptians, the Mayans, the North American Indians. I think that everyone in the old days sitting around looking at their animals or sitting around wondering about the night sky had stories to tell, and the stories were mythological or had moral character to them. And of course, gods were always ending up in the sky. Gods that were great hunters, or gods that had oracles or challenges to meet. and their dogs went with them, and you name it, they're up there. Now, our culture came from really Greece and through Rome and through the Middle Ages, and we have Greek mythological stories for constellations. Other cultures looked at the same body of stars and imagined different things, such as the Danish people thought that the Big Dipper was a wagon, and that the English people thought it was a plow, and that the Chinese thought it was 7 wise men carrying a ruler. And we think, of course, in the northwest United States, that it was a great bear. One nice thing that I like to tell is about the Milky Way, of course, that the Indians in our area in the northwest and in western Canada thought that it was raven tracks in the snow. So everyone had a different idea of what the sky meant to them as human beings. And the sky, of course, was periodic and is fairly constant, and the planets wandered all over, and of course they were given godlike freedom to act like gods, whether it was an upper world or underworld. The Mayans actually had a culture based on astronomy. The Stonehenge is astronomical, and so a lot of archaeological things have come out to be astronomically based as we study them in modern times in the last 20 years.
Kurt, we started the
Yes,
program
Tony.
with the solar system, and we know the solar system is located in the Milky Way. I'd like for you to take our viewers through a more detailed description of the what all is encompassed in the solar system, and for comparative purposes, how does our solar system compare with other galaxies and so forth that's within the area? In other words, let's go from solar system to the Milky Way, and
Okay.
then next week we'll talk about the universe. But
Well, I think have a perspective where we are is really important, and that's been one of the searches of history, is to find out who we are and what we are and where we're going. And one of those is the solar system is embedded in a larger body of about 10 to the 11th stars. It'd be like a giant pancake revolving very slowly. And on the outer edge of the pancake, about 2/3 of the way out, is a star called our sun. And our sun rotates with this pancake as it turns around. And we're locked onto the sun gravitationally, and then we have the 9 planets going around that. So when we look out into space, we're just a really small, insignificant piece of our Milky Way, which is composed of 10 to the 11th stars. That's more than I can pronounce. And beyond that is more galaxies. And so it kind of boggles our mind. Now, historically, a long time ago, the solar system was thought to be the universe. And about 1930 or so, we found out there were galaxies. So our solar system is embedded in another larger body called a galaxy. And it's built like a giant pancake, and this is what's going to get you. It's about 50,000 light years across. And when you look at a star that's very friendly and local, and you kind of associate with it and you think it's your friend, it could be beyond 4 years away. So when you look at stars in space, everything has already occurred, even though you think it's temporal, but it's many hundreds of light years away these stars are located. A very large expanse.
gives one humility when one describes it in those terms.
You feel extremely humble. Yeah.
You know, you were talking about the sun is very, very small in the context of the Milky Way.
Yes.
But then the Earth is really tiny compared with the sun. As you were describing this, we know that within the solar system are the planets that are evolving around
Sure.
the sun. And we know that there are other things that are there other than the sun and the planets. Give us a little more detail about what else we identify. And then I have a second part of the question is,
Sure.
as our technology has improved, we keep thinking we know things and then we discover new things. Is it possible there are more than 9 planets within the solar system?
Well, search, I'll go in the reverse order. The search for the planet X, or the 9th planet, or the 10th or the 11th, has always been a search for hundreds of years. And people still talk about another planet, but really it's fairly insignificant whether there's one or not. The beauty of the solar system is that you have 9 bodies going around the sun in complete harmony. The harmony is called the minimum energy principle, and they just fall into place and stay fairly stable. What other things are in the solar system? I think when you look at other planets and you start delving into what atmospheres are there, or the chemistry of interstellar molecules or interplanetary molecules, you deal not with the bigness or the expansiveness as we felt humble looking at stars, but way down inside we have to get into the idea that inside an atom is just as important to the astronomers as the large view of space. And so that brings us into the other end of the spectrum, what is it that caused all this stuff to happen, and where did it come from? And we're down, way down inside the atom. And so in the last 50 years, the study of the inner atomic ideas, or subsets of atoms, is just every bit as important as the size of the universe or the size of things. And so the solar system, it might boggle your mind, but it's tougher to boggle your mind if you're thinking about something you can't hold in your finger that's smaller than what you can think and imagine a point. And that has character and meaning to the solar system.
And a question for Lloyd, and then go back to Steve. Before the show, too, we were talking about there's so many things to cover in this area, but the Earth, the planet that's very important to us since we live here and survive here, is we talked about two things, atmosphere and we talked about magnetic field. Explain to our viewers what those two components do for our survival on the planet.
Well, they just make it possible. Without the Earth's magnetic field, which we believe is a result of a molten interior of mainly nickel and iron that has been heated with nuclear decay, the fact that we set up convection currents internal to the Earth, we have an inherent magnetic field. Now, what this magnetic field does is it shields us from the cosmic wind, so to speak. High energy radiation, very high frequency, short wavelength radiation, which would be lethal. We know, for example, the exposure of the people to nuclear disasters at Chernobyl and the effect that high energy radiation has on the human body. It penetrates, it destroys, it causes problems. And so the one shield that we humans have here on Earth is the Earth's magnetic field.
And without that, we would just get all of this radiation.
Absolutely. We would be, well, essentially all of it. Some of it may be filtered out with the atmosphere, and I'll talk about that in just a second. But this now radiation that comes to us from the sun, the parent sun, is funneled into what we call the Van Allen belts, the radiation belts, which sort of, it's a toroidal or donut shape around the Earth, and we confine these high energy radiation into those belts. They do get into the Earth's environment through the poles, where we have a lesser effect on the magnetic field, and so we see the results of that. As the cosmic wind funnels in at the poles, we see things like the aurora, the borealis, the excitation of the atmosphere to give us those northern lights. But essentially, it's a basis for our survival here on Earth. Then you talk about the atmosphere, and we're talking again about radiation shielding. You've heard the dilemma that we're faced with the demise of the ozone layer, for example, which is deleterious to us. If it's destroyed, then the ultraviolet, the out of the visible range, but certainly lethal to us humans, starts to enter. The Australian people are experiencing increased evidence of melanoma, skin cancer, because they're being exposed to these high energy radiations. So basically it's this envelope of an atmosphere around, very thin by the way, atmosphere that the Earth possesses and its magnetic field that makes it possible for us humans to survive.
You mentioned that in Australia there's a problem. Is the ozone torn there, or is it thinner?
Yes, it's being destroyed by human elements, and the South Pole, over the South Pole, it seems to be deteriorating faster than it is elsewhere. And again, that's why in the Southern Hemisphere they're being exposed to more of this high energy radiation.
Steve Sheen.
Kurt, you gave a great explanation just a little while ago when you sort of put the Earth and the solar system and the galaxy and the universe into some perspective. But I want you to back up a little bit for us less math and science literate people. You were talking about numbers of stars, and you mentioned 10 to the 11th power. Could you explain that for people who don't have a good background in math or scientific notation?
Sure. 10 to the 11th would be a 1 with 11 zeros behind it. So if you wrote down 11 zeros and put a 1 in front of it, that would be the number of stars in our Milky Way.
Big number.
It's a huge number. And here's another important thing. If you start counting today, you'd probably never count that high.
All right.
And so these are estimates from photographs, and astronomers have no hesitation on estimating. They do that all the time, and to get data and to try to work with their equations and theories, the theories of physics that are universally accepted. And some of the beauty of the universe is, or the solar system is, that the theories and the mathematics seem to support what we're looking at. And it's very important in science to have models. And that's why we're going out to planets, taking pictures, gathering data to model the solar system. It's an important idea to duplicate nature. It's an extremely challenging thing to do. One of the most difficult things is to write down something, an equation of nature, whether it's a human mind, whether it's a solar system, whether it's something inside of an atom. It's a very difficult challenge. And it's created a lot of ideas in the past.
Let me get you to define another term. We also talked in terms of, or you talked in terms of light years, which is really a measure of distance more than it is a measure of time. Would you explain that to the audience as well?
Certainly. When you think of the time it takes for light to travel from the sun to the Earth, roughly a little over 8 minutes, 8 1/3 minutes. Astronomers found out real soon after they studied beyond the solar system that this unit, called the astronomical unit, was too small. Our solar system is only minutes and hours large. When you take into consideration stars, we have to go years. So how far light will travel in a year is really a large number. I like to use the analogy that you can't outrun your light switch. 4-year-olds will switch off the light and jump in bed before the light goes out. Well, that's impossible. The light will travel around the Earth about 7 times in a second. So it's an extremely fast motion idea. And so the solar system is small in time, minutes or hours, but beyond that in the stars, it's really a long expanse. And when you start thinking 50,000 light years in diameter for a Milky Way that we're part of, and the solar system are locked onto that, you have some comforting ideas that things are huge, but we're still locked in for stability.
So light travels how fast now?
Well, 3 and 10 to the 10th. I got to get those powers of 10 in there, centimeters per second, or you could say 310 to the 8th. So it's 100 million meters per second. That doesn't have much meaning to people, and I hate to throw out numbers all the time. I'd rather tell them that light goes so fast that it goes around the world 7 times, and they kind of identify with that.
Yeah.
All right.
Because a car, 100,000 miles on a car is 4 times around the Earth, and it's no wonder they wear out. But this is twice that, 2 cars long in a second.
Lloyd, let me get you to follow up on something you mentioned earlier, too. You talked in response to Tony's question about some things that make this planet maybe unique, or at least relatively unique. We've talked about, certainly about a magnetic field.
Yeah.
We've talked about an atmosphere. And somewhere earlier in our discussion we mentioned water. In all the years that astronomers have been studying other planets, and I know that the further away we get, of course, the harder it is to be certain about some of the things we observe. But how unique is this planet in terms of those 3 essential elements of life?
Yeah. Well, water, of course, is ours, and I think the reason that we have the oceans, which was the beginning of life as we know it, really, in the oceans, is that our opportune location from the sun. We just happen to be the 3rd planet out, and we happen to be the right distance from this intense energy source. And probably when the solar system was beginning, all of the features that exist now on Earth and support life were evident in the other planets. But because of their location and because of different factors like the mass that accumulated in that particular vicinity, we end up being the lucky ones and having usable water. As we explored some of the planets, we've been to Mars, we've landed on Mars, we've taken sample of Mars. We see no evidence of water on the surface of Mars, and yet we believe that at one time water did exist on Mars, because if you look at the erosion patterns on the surface, it was some sort of liquid flow, and it's more reasonable to assume that it was some sort of water. When we look at the ice cap on Mars, which changes in its size during the course of a year, it extends itself and then it retreats. It's something like a glacier might do this. Then you have to believe that there is some source of water. Now, as we go out into the outer gaseous planets, they're so overwhelmed with some other elements and other gases that the presence of water might be suspect. But then when you look at the moons of these larger planets, and as Kurt has indicated, they're all different. Every one of those moons has a different chemical makeup, a different structure, a different history, a different look. It's incredible. And you have to believe that perhaps some water is out there, trapped in these moons. Is it Titan that happens to pick up
Triton.
Triton.
Yeah,
Triton. Ooh, boy. One of the moons that could support life, perhaps. And so if we're looking for a place to go, if we mess up this one, we might have to disperse and go someplace else and go to that. But I guess in answer to your question, yeah, water does exist elsewhere. Whether it exists in a sufficient quantity to support life, we don't know. And we'll continue to study that, of course.
And that combination of things, oxygen, water, a magnetic field to protect us from solar radiation. We haven't found anything like that yet in the solar system.
No, we haven't, Steve, and I could possibly add a little bit of insight also to that. When you deal with water, or whether it is a water, how about the other things that are there, and how about the extreme temperatures that might be considered? And so things just aren't right. And then you think about the human life on the Earth, and you figure, well, what is it that we would have to have? And it's funny that our eyes are matched to the visible spectrum of the sun. It's funny that our oxygen in our life is supportive to the response of our atmospheric composition. It's a wonderful blend and a mix. When you go to other planets and start looking for the possibility of life, you find out they're either battery acid, the pressure is 90 atmospheres, which would crush the human skull if you just stood in there for an instant. You find out there's no atmosphere, there's a vacuum that would cause you to disappear when you just step outside. So I would say, wouldn't you, Lloyd, that everything is a hostile environment elsewhere?
Yes. Outside of our environment here on Earth, there isn't any place that we can expect. Not yet.
We have less than 2 minutes, but I just have to make this comment. Lloyd triggered my thinking is that even if we found a place where we could go to live, like a moon, we couldn't afford to transport everyone there. So I would suggest we might ought to treat this planet rather nicely. We might have to use some lottery system to get decide who goes there. With less than a minute to go, tell us just very quickly, in 30 seconds, about an eclipse.
An eclipse is a phenomenon of one body in space getting in front of another. And if you have a sun and you're wanting to know what happens on an eclipse, just imagine the moon getting between you and the sun, and that's the example of the solar eclipse. Philosophically, it's been a big event for a lot of people in the world, and it happens about every 250 years in any one spot in the world. They're quite predictable. Ancient astronomers used to pay big money for people that knew that.
On that note, I have to bring our program to conclusion. I know Steve joins me in saying this has been so exciting and informative, and we have good news for the viewers that you'll be back next week and we'll talk about a really large subject called the universe. And we look forward to that. Ladies and gentlemen, our guests have been talking about the solar system, Kurt Nelson and Lloyd Marsh, and they'll be with us again next week on the universe. Until then, please have a good week. I am Tony Stewart.
The North Idaho College Public Forum was videotaped live from the studios of Instructional Technology on the campus of North Idaho College for viewing at this more appropriate time. We invite you to join us again next week for another all-new edition of the North Idaho College Public Forum on this public television station.